In this example, we consider an integral containing rational functions with irreducible factors in the denominator. So consider this example, integral of 2x plus 1 over x squared plus 6x plus 11 dx. The first thing you need to check in such examples is to check whether the denominator can be factored or not. If it is not obviously factorable, then we need to check the discriminant, b squared minus 4ac, which in this case is negative. And if it is negative, it means that the factor x squared plus 6x plus 11 is irreducible. It cannot be factored. In this case, we complete the square. To complete the square, we need to add and subtract something to have a perfect square inside. The formula for completing the square is we need to take this coefficient, which in the case is 6, divided by 2 and a coefficient a in front of x squared, which in this case is equal to 1. So we add 6 over 2 squared and then subtract it and then write plus 11, the same 11 as here, which leads to this expression with a perfect square here, which is x plus 3 squared plus 2. So we rewrite our integral in this form with the completed square in the denominator, and the word of caution, do not split this yet. If you split it now, later we'll have to do some extra work. The next step is we're going to make a substitution, u equal to x plus 3. So make a substitution u equals x plus 3. In this case, du equals dx, and x is equal to u minus 3. We're going to need an expression for x in terms of u. So in our integral, here is u minus 3. This is where x was. It was 2x plus 1 previously, and the denominator is u squared plus 2. Combine the like terms on top, and now you can split. Now, why is this integral better than the original integral? This one. Now, here in the original integral, there was x, a linear term x in the denominator, while here there is no u. And the whole point of completing the square is to eliminate that linear term with u in the denominator. So now we split it into two integrals, and each of these integrals is relatively straightforward to find. The first integral with the u on top, after a substitution w equals u squared plus 2 will lead to natural logarithm, while the second integral is a straightforward arctangent integral. So make a substitution, w equals u squared plus 2 here. dw is 2u du. Make the substitution. It leads to a natural logarithm of absolute value of w. Now back substitute u. W is equal to u squared plus 2. We don't actually need to keep the absolute value sign because the expression in the inside is always positive, so we can replace it with parentheses, although it's not a mistake to keep absolute value here. So the first integral becomes natural logarithm of x squared plus 6x plus 11. Now I don't write plus c because I will write plus c in the end. The second integral is 5 over square root over 2 times arctangent of u over square root over 2, and pay attention to the fact that this is square root of 2, so the square root of this number rather than this number itself, and back substitute u equal to x plus 3. It becomes 5 over square root of 2 arctangent of x plus 3 over 2. So our integral, which is a sum of two integrals, this and this, becomes natural logarithm of x squared plus 6x plus 11 minus 5 over square root of 2 times arctangent of x plus 3 over 2 plus c. That is the final answer. And also pay attention to the fact that this logarithm contains x squared plus 6x plus 11, which is exactly what we had in the original integral on the denominator. And this will always be the case.